Hey everyone! Today we will be talking about measuring non-Newtonian samples. I'm Ashley.
And I'm Julian. Today we're going to start with a little presentation from Ashley about some background about non-Newtonian samples in general. And then we're going to follow that up with measuring non-Newtonian samples on two of our instruments, the microvisc and the VROC 2. All right, now over to Ashley for the presentation.
So today I just want to start out with talking about how we can measure these non-Newtonian samples with VROC technology, as well as why are these samples, in a general sense, shear thinning or shear thickening. So to start out, before we even get into why this is happening and how we test this, I want to talk about some main terms that I'll be using in this presentation as well as throughout this webinar. And so first, you might hear us say shear rate, and this is just the rate of deformation. When we speak of non-Newtonian fluid, which I just mentioned, that's going to mean that viscosity is dependent on shear rate. If it was a Newtonian fluid, as you change shear rate, viscosity would not change. More specifically, non-Newtonian fluids can be broken up into shear thinning and shear thickening liquids. Shear thinning means that as we increase shear rate, viscosity will decrease. Where thickening is the opposite, we increase shear rate, viscosity also increases. When I say critical shear, I'm talking about the onset of this shear thinning or shear thickening behavior. A lot of fluids first will look like a Newtonian fluid, but as you ramp up shear rate, will suddenly become non-Newtonian, and that's where we'd call the critical shear. Finally, the units I'm going to be using throughout this presentation and in this webinar are centipoise, which is the same as millipascal seconds. And these are dynamic viscosity. So first, I just want to get started out with an example of shear thinning behavior. Shear thinning is quite common in things like biologics, biological fluids. And so here's an example where we have some BGG, and at the same concentration, we've just added an excipient. And so without the excipient, we'll see that initial viscosity is higher, but also the shear thinning profile, where it starts to change viscosity as shear rate increases, is also different. The one without an excipient is shear thinning at a different rate than the one with an excipient. And so when we think of excipients, it's important to not think of them as just a viscosity modifier at a single point, but rather changing its entire rheological profile. So here's another example, but this one, instead of looking at an additive, we took the same sample, but we just changed the temperature. And so you'll notice that temperature drastically changes viscosity. But again, it doesn't just drastically change the viscosity at one point. It doesn't just go from 90 to 35, but rather changes when it shear thins. So if your sample is delivered at 10 degrees Celsius, it is going to begin to shear thin at a quite lower rate than if it's delivered at 37 degrees Celsius. And so that's why it's important to look at these samples not only under different conditions of temperature, but under different conditions of shear. So why do we see this shear thinning behavior? Well, of course, there's lots of reasons, and it depends a lot on the sample type we're talking about. But some of the major reasons your sample might be non-Newtonian, changing as it changes shear rate, is the alignment of molecules or particles as they push against one another. It could also be the breakdown of internal structures. It could be due to a reduction of intermolecular forces, for instance, going from thermodynamics dominating to hydrodynamics dominating, or it could be changes in microscopic flow patterns. This would be more relevant in other systems where turbulence is relevant. So here is an example of a shear thinning profile. And this one is, of course, of monoclonal antibodies. We see that classic low shear plateau, whereas we change shear rate, viscosity does not change. But then we see that critical onset where thinning starts taking place. But a sample can't have zero viscosity, so this can't go on forever. So eventually we see a second plateau, and this is the high shear plateau. And yet again, as we change shear rate, viscosity does not change. So why do we care about this shear thinning behavior, shear thickening behavior, or even Newtonian behavior? Well, part of it as you're formulating your different types of samples, you're going to change different ingredients. You might even change what temperature the sample should be used at. And when you do these changes, these interactions and microstructures inside of the sample are going to change. And that is going to directly affect viscosity. And as we've mentioned before, this isn't just going to affect viscosity at a single point, but the entire rheological profile. And then once you get that information, maybe you find out this isn't the right viscosity at 100,000 inverse seconds, which is what is relevant to my sample. So now I'm going to go back to the formulation. I'm going to change it again, which is going to change these interactions and microstructures and change viscosity. So you might be asking, how can I test this? How can I test what my sample looks at 10,000, 100,000, 200,000 inverse seconds? Well, we do this quite simply with VROC technology by flowing in our sample into this inlet, and we pass your sample across 4 pressure sensors. These pressure sensors are going to measure the drop in pressure, and then your sample flows out to a reservoir or a waste container. We are precisely controlling this flow rate with a pump, and we know the dimensions of our flow channel. With that information, we are able to calculate shear stress and shear rate, divide shear stress by shear rate, and you get dynamic viscosity. So that is how we are able to test your sample's rheological behavior. Now we're able to test at these really high rates, 100,000, 200,000, because of this microfluidic channel. We do not have to worry about things like turbulence. So thank you for listening to this portion. Next, we'll go on to a demo on how to test.
The sample that we're going to be measuring today is 0.5% medium molecular weight hyaluronic acid. We're going to be measuring on this microvisc chip, which is a B05. I'll just load that up into the system right now. Turn it on. Load up my sample. Now we'll go into advanced mode and pick our starting shear rate, 500 inverse seconds today, and hit run. Now that sample is going to run on the microvisc until we have a complete data point, and then I'll go back to that advanced measurement screen, set a new shear rate, and then I'll repeat that process until I have every shear rate that I'm going to need to build a complete viscosity profile at a full range of shear rates to see that non-Newtonian behavior.
Alright, so now on to the VROC 2. Here the chip is going to look a little different than with the microvisc. We still have that chip that holds the microfluidic channel, but what we think of as a chip package also includes this reservoir. The reservoir is going to let you test one sample volume an unlimited amount of time, and then we also have reusable syringes with the VROC 2. Here's the 100 microliter syringe. We also offer a 2.5 ml syringe. So now I'll place it into the instrument and everything else is done on the software. So once the sample is loaded into the instrument, you have to set up your experiment using the software. So here we set up an experiment where it goes through different levels, which will correlate to different shear rates to test our sample. This will test if it's Newtonian or non-Newtonian, as well as the non-Newtonian behavior. Some differences from the microvisc is this will be much more automated. Rather than having to type in each individual rate when the last measurement ends, I can set it all up all right here, press run, and go do something else while the shear rates are being tested. Here we can see that the system is testing at different shear rates using the same loaded volume. That means I don't have to worry about running out of volume and reloading the syringe. I can set it and forget it.
So now that we're done measuring our HA sample on both the VROC2 and microvisc, let's look over the data we collected. Starting with microvisc, I just exported the data from our software into an Excel format so that I could show you guys here. I highlighted in orange our viscosity values, and then in blue our shear rate values. So you can see that I started around 550 inverse seconds of shear rate, and at that lower shear rate our viscosity was around 40. And then I progressively ramped up the shear rate by 50 each time over 40 different runs, all the way up to 2,450 inverse seconds. And at that much higher shear rate, our viscosity dropped all the way down to just 25 millipascal seconds, or centipoise. And that gives us a really good indication of the behavior of our sample at that wide range. And then just understanding this viscosity profile gives us a really good picture of how our particular sample is going to be behaving differently at different shear rates. Now let's hop on over to the VROC2 data. So on the VROC2, we measured with the same microfluidic flow channel type. Both on the microvisc and VROC2, we used the BO5 microfluidic flow channel. But on the VROC2, the pump is a little bit stronger, which is going to allow us to hit higher shear rates. But if we look a little more closely here at the data, we can see a very similar story. So at those lower shear rates, starting at around 500 like we did on the on the microvisc, you can see we're hovering right around 40, and then as we increase shear rate, we're seeing that drop off towards 25, around the 3,000, and then going even beyond that all the way up to what looks like 6,300 inverse seconds. And you can see that non-Newtonian behavior, that shear thinning behavior, keeps dropping our viscosity as we increase the shear rate. So we got a little taste of that full profile on the microvisc, but we can see that behavior goes even beyond. And so this is just highlighting that it's really important to understand that non-Newtonian behavior that you're going to have in your sample, because it can drastically change the viscosity depending on how you're delivering your particular sample.
As you can see, measuring non-Newtonian behavior on all of our instruments is very simple with VROC technology. Thank you for watching.